Okay. So, just one technical thing. Do you prefer, since I've seen I'm the only one, do you prefer that I start here writing or prefer something in between? Like in between, right? Like from here. I know. Half. Okay. Okay. Yeah. Right. And then something like that as well. You guys here. Okay. So let us recap briefly what we have seen about the Kraichnan model last time. Okay. So remember we are talking about. Okay. So far we have considered covariance matrix Q, okay, which is given in Fourier modes by the following form. Identity with alpha parameter. Okay, most of the time will be smaller than 1. Okay, and this is just the 1 plus n squared 1/2. Right, and we have taken a vector field V, okay, random vector field, okay, vector field. Okay, actually distribution valued, right, in time, because that also was mentioned in the talk before. It was distribution valued, right, white in time, which is a Gaussian centered, meaning 0, centered, okay, and with covariance matrix given by the following form. So white in time and covariance matrix Q in space. Okay, we have seen some properties, this is isotropic, divergence-free, and so on. Right? Then we have considered the associated dynamics. So the x, roughly speaking, we can write this way. V. Okay, let me see. You can think of as x dot equal to v t xt. Informally, rigorously, this is the x equal to, let's say, the Stratonovich dw tx, or if you want, sum over k of sigma k x Stratonovich dwk, where sigma k satisfy the relations okay, right? And wk, of course, are 1D IID Brownian motion. Okay. Right, and we have considered also the associated DSD, the associated stochastic continuity equation, which takes the following form. Let's write this way. I mean, sorry, there is no B. Sorry. You can write this as the following. Like informally, again, you can think that this is just this, and more rigorously, this is this. That's the divergence. Okay. And we started doing some computations, right? So the computation that we did, we said, okay, let's consider the law of one particle, the one-point motion, and we saw that this satisfies basically in law. It is essentially, well, let's say I can say x is essentially a Brownian motion, d-dimensional Brownian motion. In law. So the single motion is just well understood, it's a Brownian motion. Let's now consider the two-point motion. Okay. What have we said? Well, let's take the difference, we call it U. And this satisfies a closed equation, which is, okay, perhaps I can write. Can rewrite dB for B, d-dimensional Brownian motion. So satisfy a closed equation. What's even better, the distance of two particles satisfies a closed one-dimensional SD. Perhaps I can rewrite here. Well, okay. Let me see if I find here. Okay. Closed one-dimensional SD. And for this SD, as I told you, we know everything. So that's the advantage of having this Kraichnan model. We can actually compute everything. And then we consider the non-smooth case. So this is true, at least formally in general. Now we consider the non-smooth case, so namely when alpha, the parameter alpha is between 0 and 1, which means that, let's say, V, or more precisely, this was also recalled in the previous lecture, W, which is the integral 0 to T to V, so W Tx, Vsx in the S. This is actually C alpha minus, right, in space. Right. Okay, so this is definitely, we cannot say, we cannot apply classical Cauchy-Lipschitz theory. And okay, we can ask whether we have still some form of uniqueness just by looking at the distance of 2 points, 2 particles starting at the same position. And what we saw by these things that, so if we start, let's say, I mean, this is technically not exactly true, but believe me that one can make it true. If you start with U0 equal to 0, perhaps I can rewrite the SD just to make it clearer. Okay. Right, so this is here. Here we go. The U, it is basically D minus 1 beta L beta n, sorry, beta n U to the power Q alpha minus 1 dt plus square root of 2 beta L U to the power 2 alpha dB for a Brownian motion, B tilde, one-dimensional Brownian motion. Where here I recall you beta L and beta n are coefficients, well, calculate, perhaps I can write, what one can say is that Q of x is up to lower order term, beta L x to the power, sorry, Q of 0 minus Q of x is actually beta L x to the power 2 alpha, x orthogonal of x squared plus beta n x to the power 2 alpha times I minus xx transpose over x squared, and beta L and beta n are related by the relations this one plus 2 alpha divided by d minus 1. Okay. Anyway, doesn't, okay, so we have seen there is this SD, and then we can say, morally speaking, that if U0 is equal to 0, then Ut is larger than 0 for every t positive with probability 1. Okay. The exact result is slightly different, but morally this is kind of true in this context. This is related to the study of this SD. Okay. So the consequence of that, as we have said, at least formally, that if we start with for the continuity equation, the evolution of the mass, the pathways evolution of the mass, if we start with the Dirac delta, at least formally, right? So we start, all particles are close together in a point, then they start to split, right? And so the mass will, the mu t will be not a Dirac delta. Okay, this is something anomalous because for an SD and so for an SD you expect to have one single, if the SD has smooth coefficients, you have one solution for each initial condition, and that is to say, if you start with all mass at 1 point, you just expect to follow the path, right? So you have still the Dirac delta as a solution. Okay, and then, okay, this of course may raise the question, perhaps since we have the whether we can define in a unique way the dynamics, right? Because of course, I mean, usually when you have no uniqueness in the deterministic setting, at least you cannot really. It is not unclear exactly. I mean, there are different possible solutions, and you don't know how to choose, right? This is in a way true also here, in the sense that if you have one, you cannot choose one of these paths, right, of the path that will leave from one point. But what you can still ask is whether there is a unique way, a unique evolution of the mass, which is not a Dirac delta, but perhaps there is a unique evolution of the mass in some way. So we can still ask ourselves whether this continuity, stochastic continuity equation has a unique solution or not. Okay, and the solution is yes, it has a unique solution. Right, so this was perhaps point 1, like particle separation. Point 2 now is well-posedness. To the Eulerian model. Or Eulerian. Eulerian model is just a fancy way to say continuity equation. Okay, okay. Now this is what I'm going to say is basically based on 2 works by Legendre and Raymond in 2002. I will give and by A and Van den Eyden in 2001, right? To put this in fully rigor, I think I would need 1 hour or more, right? So I will not do exactly all the details, right? But I try to give the idea, even perhaps giving the statement which are not exactly what as they state, but just to try to give some idea about how it works. Okay, so let me start with the one remark. Okay, the model is, so we have seen that we have not one solution, one single solution, but what we can say definitely is that there is already some well-posedness in law, right? So luckily this was the uniqueness in law concept were recalled in the previous talk. So anyway, so we have seen that the one-point statistics are well defined. This is just they are well-posed, are uniquely determined. So it's just d-dimensional Brownian motion, right? So we have some form of like well-posedness of sort of one-point law. Okay, so the law of any particle xt x must be the Brownian motion. Okay, Brownian time t if you want, right? D-dimensional Brownian motion. But in a way, actually, we have well-posedness in law, I should say, otherwise it's right. And we also have well-posedness in law, actually, also of the 2-point motion. Okay, 2 point. If I write this, if I have well-posedness in law, perhaps I can write here motion. Okay. Why is that the case? Because sigma k, I've told you the coefficients are not Lipschitz, so why it should be true? Well, let's have a look to the equation for the distance. The distance itself, it satisfies an equation which, yes, it has a singularity. This q has a singularity, but only at 0, right? Because have a look to this form. I mean, I've not proven yet, but look to this form. The only singular point, the only point where this is the square root of this is non-Lipschitz is basically when x is 0. So outside 0, everything is fine. You can actually prove as an exercise that this is actually true also for the 2-dimensional, the 2-point motion itself. Actually, you can say that this is, roughly speaking, this is the square root of a block matrix, which is made in this way. Or some, say, okay, B2 perhaps, which is a 2D-dimensional Brownian motion. Okay, and perhaps there is a factor 2, I guess, here. So also here, you see that the problem is that this is actually smooth outside the diagonal x equal to y, but, okay, so this means that as long as you don't touch the diagonal, you are essentially happy, right? But the point is what we are saying in this statement is that we are never touching the diagonal, right? And actually, even if we start on the diagonal, then we will leave the diagonal immediately, right? This is not a full proof, but in a way, so we are saying that this law here is uniquely determined. determined. Right? Right? And so this is due to this and the fact that x, y does not touch the diagonal. Sorry, yes, x, thanks. Yeah, sorry, here there should have been, yeah, thanks. Xx minus xy, xx minus xy, sorry. Xx, xy, this is xx, xy. Okay. Right. Okay. So something tells you that not everything is bad, but I mean, there is some well-posedness, though you don't have Lagrangian, so pathways uniqueness. And indeed, this is the first argument, if you want. This is due to, they don't write all details actually, but A and Van den Eyden. Yeah, I hope the spelling is correct. It might be some, it doesn't one. There are actually two papers. One is on Physica D, and one is on PNAS. Okay. They study mostly the two-point motion, and then they obtain something, right? So what they say is that, okay, essentially from these things, we get theorem. Okay. It's not exactly what they get in a way, but again. Yeah, okay. Well, actually, okay, I'm sorry, let me be slightly more precise because otherwise. Okay, yes. I think if I can say. Okay, so yeah, no, let me say this way. So it's true also more in general, but I don't want to. Let me take now mu nu solution to kind of viscous PDE, stochastic PDE, which is this. So one way to deal with this problem, of course, of well-posedness is to say I just add some viscosity. Right? And then Stratonovich dW. Okay. And I add some viscosity, and then of course I want this mu to goes to 0. And they result, let me put it quotation mark because it's not exactly the result, I'm just extrapolating more or less, is that essentially mu nu converges to a unique limit mu, right? Okay, what's the idea behind is that it is based on the 1 and 2 point motion, right? And the idea is the following, okay? Okay, well, okay, it's unique limit mu, which satisfies, sorry, I forgot one point, which satisfies the stochastic continuity equation, right? Okay, let me not give the full proof, but kind of the idea. Proof. Okay, first of all, one can show that you have convergence of 1 point and 2 point motion. Okay, what I mean by that is that you can show that. Okay, sorry, I should have perhaps let me state in. Okay, so what one can say is that. Let me think if there is a perhaps easier way to explain this. Otherwise, yes, it's. Okay, let me slightly cheat and give a shorter kind of proof, but which is basically the main idea. Okay, let me take mu any limit point of mu nu, right? Okay, now the point is we know that the 1 and 2 points motion are uniquely determined. And the basic idea is that once you know the 1 and 2 point motion, you know the solution to the stochastic continuity equation. Right? So the idea is that mu is uniquely determined by the 1 point and two-point motion. By the way, this is the, actually I can say more, this is actually which is the unique solution. The unique solution to the stochastic continuity equation. Okay. Why it is the, so the idea is that basically once you know the two-point motion, you know it is unique, then you have a unique unique evolution of the mass. And why is that the case? Well, they don't write the proof, honestly. I mean, I'm sure that they have in mind because they said it is enough to show this, but where I left my, right order, thanks. Okay, I think I can do even without. So the point is the following. So let us consider mu and mu prime. Sorry, perhaps this is not. Two limits point, two solutions to the stochastic continuity equations, right? Okay, now we want to prove that the mu tested against any test function phi is the same of mu prime tested against any test function phi. Okay, this is what we want. Okay, now so let's take phi d mu minus phi d mu prime. Remember, this is not random, but mu is random, right? It's a random evolution, so it is random. This is, of course, I mean, I should put here a t because they depend on time, but okay. Right? Think of as a random measure, right? Then, since these are random, to prove that they are equal almost surely, let's say, right? Almost surely, then I can take the square and I can take the expectation. Fine. Let's see what these are. This is the expectation. Let's develop the square. So I can write this as the integral of phi d mu minus mu prime. Let me forget about the t, I don't care. This is now becomes, I can basically, when I take the square of these things, I can just double the variable. I can have phi x, phi y d mu times mu, mine plus mu, then you just develop this. So this is mu times mu plus mu prime times mu prime, minus mu times mu prime, minus mu prime times mu. So if you want, in x and y. But what's that? That's exactly the two-point motion average. So recall that the formula that I've written yesterday, that phi xy, sorry, psi xy, mu times mu dx dy is in expectation. This is exactly the expectation of the two-point motion. Let's say, okay, yes, x, I should say xx, xy, mu 0 dx, mu 0 dy. Think for the moment, though it's not, let's say, mu 0 is just the Dirac delta, right? So it becomes exact. Okay, no, it's not even needed. Okay, the thing is, the same is actually true for mu and mu prime, for any two solutions. That doesn't need to be the same, right? You can, I mean, this means just that you start with two solutions. But then what we are saying, all these two objects are basically the expectation of phi xx, xy. Okay, minus 2, the expectation, these two objects, say these two are also the same, right? I wrote this one, so minus 2 phi xx, xy. All should be integrated perhaps in, sorry for this, this is mu 0 dx, mu 0 dy, sorry, I have to go, the graphics is not fantastic, but this is the integral, right? And so this is just 0. Fine, this proves essentially the uniqueness of the evolution. So the main message is once you know how to control here the one-point motion and the two-point motion, then you know how to control, then you know the solution, you know how to control the evolution of the mass. That's basically the main message. Of course, I cheated here a little bit. Why? Because I can say I have in principle to prove, if I want to be fully rigorous, I have to prove that mu, any solution mu is actually does satisfy this formula, which a priori I don't know. So and that's why actually I need some form. It's easier to work with the limit as null goes to 0, right? But again, I think the idea is roughly that one. But there is a second proof, okay, which is due to Legendre and Raymond. In a way, it's different proof. It's really different. To me, it's kind of a different argument, and they work in situations, possibly in different situations. These two, I mean, besides the incompressible Kraichnan, which is basically, which is telling the following theorem. Again, it's right. There exists a unique Brownian adapted. Brownian adapted means strong, probabilistically strong in the language of the previous talk, and the language, usual language of probabilists. Means I don't want to add more information than the Brownian one, right? Technically, okay. If you want the definition, which was already given in previous talk, but so to say, just to recall, this means that mu t is sigma of ws for s smaller than t measurable. The exact definition, but okay. It's not so important. It's not even so important in the. I mean, it is in a way, but that is a mu solution to the stochastic continuity equation. Now, this seems a slightly weaker statement in a sense. It is because here this is uniqueness is not restricted to Brownian to strong solutions, right? But it works under a kind of weaker assumption in a way. So idea of proof. Okay. By the way, how many of you have seen Wiener-Krauss decomposition? Don't worry if you have not. I guess I don't believe that all of you have seen Wiener-Krauss decomposition. How many of you have seen Wiener-Krauss decomposition? Okay, yes, that's what I expected. Of course, you don't need to know this. So the idea is essentially this one, that let's consider the Fokker-Planck equation, the associated Fokker-Planck equation. Okay, this is dt rho plus, okay, recall that this is basically the average of the continuity equation in a certain sense. Okay, when recall that I can write this equation here, where the equation I forgot, so perhaps I'll write here the equation, dt mu plus divergence, sum over k of divergence of sigma k mu Startonovich dwk equal to 0, but I told you, well, I can write this as a Ito integral plus remainder, and this remainder in this case turns out just to be, roughly speaking, a Laplacian, because this is the second order correction. If you take the average, the Ito disappears, and you just get the heat equation. Okay. Right. C is just that Q of 0 is just C of identity. Right? Okay. And now the main idea is the following, that once you have uniqueness of the Fokker-Planck equation, this implies Brownian adapted uniqueness for the stochastic continuity equation. Okay. This is something kind of magic, because the uniqueness of the Fokker-Planck is related in a sense to uniqueness of one-point motion. We are not using here the two-point motion. Nonetheless, we can select in this way the unique solution, as long as it is Brownian adapted, to the stochastic continuity equation. Okay. It sounds a bit of magic how the proof works. So why one can, so okay, uniqueness of this is very easy. This is just the usual heat equation. It's super classical. Why this is true? Okay. Well, I don't want to do the proof because it is needed Wiener-Krauss decomposition. It does not make sense to do right now. I just want to kind of give an idea of it. So the point is, you want to decompose the space of solution, functional space. Let's say R2. I want to say in R2, uniqueness in R2, of time, space, and omega. Not sure that time is needed, but as a direct sum of subspace En. And I can take the corresponding projection in such a way that the corresponding projection pi n satisfies the following two key properties. Pi n of gx, this is a random variable, right? Because there is a random fields in a certain sense, right? There is a random variable. If I multiply this by a deterministic function, g deterministic, this is going to commute. Okay? And what's more important, if I apply pi n to a stochastic integral of x dw, this is going to be the stochastic integral of pi n minus 1 x dw. Right? So using these two properties, you can reduce the uniqueness to the stochastic continuity equation. And by the way, this projection is, and why I use adaptives here, I actually work on the space of Brownian, subspace of Brownian adaptive. Sorry, this was important. So, not just L2, I cannot take L2, I have to take, does not work, Brownian adaptive. Right. So, as long as you consider Brownian adaptive, there is such a composition in subspace such that when you take the projection, these two properties are satisfied. And then this is just a uniqueness. You can reduce uniqueness. You can do as an exercise. You can prove this as an exercise out of these two properties. It is essentially up to details. It is essentially an induction, proof by induction or by recursion. Sorry, not by induction. Right? You start with the actually. Sorry, pi 0 is the expectation. Right? Pi 0 is the expectation. Anyway, if you don't know, just take this as a fact. So as I told you, this is there are two kind of different lines. One says I first know the two-point motion and then I identify the evolution of the mass. The other one, I say I only know essentially the one-point motion, and I'm able to select in a certain way a solution to the stochastic continuity equation. Anyway, we will see also a third proof of uniqueness later on. And they can be applied, just as an information, they can be applied also to more general random fields, especially in the compressible world, right? But giving different result. So in the compressible world, the Legendre-Raymond argument works. This one kind of also works, but it produces, I mean, for example, you can ask what happens if you regularize sigma and do not take this. You get a different limit in some regimes, right? The compressible, in the incompressible, okay, so anyway, that's just to say the two argument can be applied also to more general context. Yes, sure. Yes. Yeah. Uses unique. Yeah. Sorry, go ahead.
So it seems like even for more regular.
Actually, in a way, yes. So as long as you have, I mean, depends on what you want to prove in a sense, right? So as long as you have uniqueness of the Fokker-Planck equation, which you can have for more general drift and diffusion coefficients, you do have a selection. You do have this stochastic, this unique solution to the stochastic continuity equation. Okay, I was a bit sloppy about the space. Depends on the space. So usually this works very well in Hilbert space. So actually, this works like in space like L2 in the space of measure. This is slightly, it's not completely clear. In fact, they result. That's why I say it's not exact. The same statement is in L2, right? On the other hand, of course, you know that you have one selection, but perhaps you would like to say something about these selections, and then it boils down to study the two-point motion. I mean, in the end, the answer to your question is yes, it works. Which solution you select, in the end, perhaps you want to study the two-point motion, and they also later on they study the two-point motion as well. I'm sure this okay. Okay. So Now, let me just state a couple of facts and then we pass to other topics about this Kraichnan model. I want to mention a couple of properties which are relevant, but I will just for say cultural reason, but I'm not going to use those. Okay. So, yeah, one thing one property that it's kind of also related to what we are seeing is a kind of third properties, anomalous regularization of two-point motion. And these the references perhaps are to an unpublished paper by Henk C in 1996. I think it's a nice, but yeah, this is and then the paper by Hakulinen in 2003. Right? And basically what that amounts to say is that if I consider the function, the semigroup, so to say, associated to the two-point motion, the expectation of phi of xx, xy, right? T, sorry. This one has smoothing property. Right? Which is something anomalous because if you, let's say, if you start, if this were smooth, if you start on if you have phi which is no smooth on the diagonal, if you have the smooth situation, then if you start on the diagonal, you stay on the diagonal, right? In the smooth case, and so you don't have regularization. The fact that you have smoothing is somehow related to the fact that you have splitting, so that you leave the diagonal and you have some form of averaging. Okay, related to x, y, not seeing the diagonal. Sorry, fourth properties, right, is anomalous dissipation, actually very, very relevant in this context. Anomalous of the Kraichnan, of L2 norm. So in a classical continuity, stochastic continuity equation, as well as in any deterministic one, formally speaking, there was, okay, let's say continuity with divergence free, sorry, as it is here. Formally speaking, any LP norm is preserved. This we have said, I have seen this more than once in the series of lectures. But and I mean, it was one of the points in the talk that we saw by Laszlo, is that in some sense we can have, I think the first one, we can have the anomalous dissipation of, I mean, whether this is true or not. Well, Font is also, yeah, it's also, sorry, it's also on Sager conjecture and so on, related to on-Sager conjecture and so on. And there is a remark in the paper, or I think already quoted by Spontaneous, that spontaneous stochasticity implies dissipation of L2 norm. This is due in a paper, in a quite general context, not Kraichnan, it is general, and this is a paper by Drivas and Henk again in 2017. But this, for the Kraichnan model, such an anomalous dissipation has been proven quantitatively, so quantitative statement, by TIFR-CAM in a pretty recent paper, Rowan, which appeared in 2013. I'm not sure it's, sorry, it's last year. I'm not sure it has been published yet, but they prove, I think, an exponential decay of the L2 norm, right? On the torus, technically, so it doesn't work exactly with the Kraichnan one, but more morally, yes. And last property, which is also of a lot of interest for physicists, is what in the language of previous talks was called intermittency. Okay. So the point is V, let's start with consider the velocity field V. P, I recall you, we can write also this way. This is a Gaussian. So no matter how much irregular is that, this is not intermittent. Okay? What do I mean by that? If you take the expectation of Wtx minus Wty to the power p, okay, this perhaps will be bounded by x. I'm doing this in x, but can also be done in time, with respect to time. So bounded by some constant times alpha p. Some constant, of course, may depend on p. Right? So in the language of definition of intermittence, which I think it was given in one of the first lectures, actually the first lecture that we saw. So the exponent, the intermittence exponent, the exponent is alpha p. So it scales like linearly with p. Okay. But this is not true for the solution. So this is so solution is not intermittent. And this has been proven. Well, there is also a paper going to this direction by Kraichnan in '94, and then it has been published in proven by physicists. I'm not sure how much. I mean, they don't. Of course, they don't care about certain things, but by Gavetsky, Kupiainen in 2019. So just 2095. Sorry, and there are also other paper. One by Sorry. Yes. Yes. Sorry. Thanks. Absolutely. So I mean, so it's not the Gaussian is in. Oh, sorry. Yes. So the Gaussian is not intermittent. The solution is intermittent. Thanks. And Chertkov et al. In 1995. Not an expert of that, but just to mention, they studied for the two endpoint motion, and out of that they get an anomalous scaling, anomalous in their language, and they prove this kind of property. But I'm not an expert. Okay. Just one thing, I forgot to mention one important reference about this kind of spontaneous stochasticity. The first paper where this kind of appear in physics is Bernard. This is all not my work. This is Gavetsky and Kupiainen in 1998. Okay, so I'm not sure it was also a little bit known before, but okay. So, sorry, what do you mean by? Yes. So, in which sense you're? The range for alpha. Alpha is between 0 and 1. No, okay. Perhaps I didn't get the question. Okay. Right. So so this is okay. So the take-home message for the Kraichnan, this concludes the Kraichnan. So we will see an anomalous regularization properties, which will follow in either today or tomorrow, which is valid. So in a way, this is does not fully conclude the Kraichnan part, but at least now I want to pass to study Euler plus Kraichnan, okay? But the main take-home message that this is a toy model, of course, driven by a Gaussian white in time homogeneous vector field, non-smooth in space, right? Which it exhibits where you can do computations because you have your SD for the two-point motion. And it exhibits nice in the sense that, I mean, features. Due to this fact, essentially, you can prove that these exhibit on one side spontaneous stochasticity, on the other side it has still a unique solution to your unique. So the evolution of mass is actually well-posed. This evolution exhibits spontaneous stochasticity, plus then other properties like anomalous dissipation, intermittency, and so on. Okay. Okay, questions so far? Yes. Yes. Good question. I think so. Okay. I'm not an expert of that. I remember what I can tell you is a discussion that I had once with Dario Vincenzi, who is one of the physicists who discovered this, and they said one of the main interests is exactly so to see whether the intermittent behavior that you observe, as far as I understand, in turbulence comes from the intermittent behavior of the, the intermittent behavior in the scalar field comes from the intermittent behavior in the velocity field or not. Okay, these as well as, however, I mean, this was much before the works of convex integration and so on, but these in a way, so I mean, perhaps in a way, now we are also answering, you are also answering to these questions in a way, but this in a way is a way to answer negatively, so to say that the velocity, the intermittent of the passive scalar does not necessarily come from the intermittency of the velocity field. Okay, that's why. So the answer should be yes, you observe, you expect it to observe, but honestly I cannot say much more, right? So I say, okay. Other questions? Okay, let me now pass to, I think, the final topic or of this series, which is regularization by noise for QD Euler with unbounded vorticity. Okay, I think that's a good point to make a very small recap of what we have seen for regularization. So now there was this kind of digression on Kraichnan model, which is not about regularization by noise per se, but as we are going to use now, this was needed because we are going to use here the Kraichnan noise to regularize. Okay. But it's good, convenient, since we now are coming back on the regularization by noise topic, is good to have a small recap. So we have seen that if you take a finite dimensional SD with a non-smooth B, so non-Lipschitz, and we add noise, then we get well-posedness. In a suitable sense and so on. And then we talked about the stochastic, well, we talked about the transport equation, but essentially when everything is divergence free, they are the same. Stochastic continuous stochastic transport equation, so this is dt mu plus divergence of B mu, plus, in this case, this is relatively simple, this is just mu. Let me write divergence of mu. Yes, I just want to write this, okay. dw is equal to 0 here. Sorry, I'm using the same notation for many different things. W is just a d-dimensional Brownian. And this is also well posed, contrary to the deterministic case. Why? Because just because, morally speaking, because this is the equation of a Lagrangian of an evolution, the Lagrangian evolution, which is well posed. Right? This is the Eulerian counterpart of the Lagrangian evolution, which is well posed. Okay. Now the question is, what happens in the nonlinear case? Okay, this is all B is given. Okay. Now we are going to consider the case where B is not given, and it depends on the solution itself. And I mean, one can consider several cases. One can start with Burgers, for example, but for time restriction, I will not. I will directly start with the case of interest, which is two-dimensional Euler. Euler equation. This would be kind of, let's say, first topic one. Okay. How much time I have? There's no 45 minutes. Okay. No, because there's no such. Okay. Okay. So wait a moment. Okay. So I don't think it is. I think I can directly write the equation in the vorticity form. Okay, so this one, u times grad theta equal to 0, so kind of a transport. Of course, here U is divergence free, so I can write this as d u theta as well, so it's transport or continuity. So this is deterministic so far. I will add noise in a moment. But then this is nonlinear because U is related on, let's say, on time and the full space, R2. This is related by the vorticity. Sorry, theta here is the vorticity. Right, field, and U is the velocity field, which of course is vector valued. Okay, and is related to the vorticity through the Biot-Savart law. So here K, X is up to a factor of 1 over pi, which I never remember. Should be basically X orthogonal over X squared. This is the, perhaps I better write another line. This was already mentioned in last talk yesterday. So mostly, of course, in 3D you have a stretching term, but we don't care here. Here we are focused on the 2D case. So this is formally equivalent to the equation to the velocity, to the equation, the classical Euler equation in 2 dimensions for the velocity. The vorticity expresses how much the fluids rotate around certain points, at least in 2D. Right? And it is convenient because this is now a scalar equation, transport equation or continuity equation, with, however, nonlinear and in a way non-local, because the velocity field depend on the vorticity field, can be recovered from the vorticity field via the Biot-Savart. Okay. Now the problem, as you see here, since U is the convolution of theta with the kernel K is smooth except in 0, where it diverges like 1 over x. So it is intuitively clear, that the problem with this equation, except okay, is that when you have concentration, don't take it of mass. I consider the vorticity sometimes as a mass, right? Just because this is a continuity equation. Okay. And by the way, I should have said, okay, yes. Okay. For example, okay, one thing that I should have said, of course, is that this can also be written as, U can also be written here. Okay, is also, let me say, the orthogonal gradient of the green kernel of the Laplacian. So in other words, and so this can also be written as the orthogonal gradient of minus Laplace minus 1 of theta. Right? So in a way, U is 1 degree more regular than theta. This is also because, okay, theta is also the curl of U. I didn't write, but right. Okay, so this is quite clear. Except, of course, when you have the infinity situation and so on. So in particular, so to say, if theta is an LP, then I expect the velocity to be in W1P, right? For P at least between 1 and infinity. Strict. Okay. Now, as it was mentioned, of course, this is actually 2D Euler equation was also mentioned in I think the first talk by Lazarus, is actually well posed, right? So in a sense, one can say in a suitable class, right? Which is the Udovich class, the class of L infinity. Well, slightly beyond, but the same infinity. Okay, so this equation is well posed, deterministic one is well posed in L infinity of, say, time and space. Right, so in L infinity, I mean the vorticity, sorry. So, and theta is there. Okay. For any theta 0 in L infinity. Okay. And so, actually, in a sense, you may say, okay, perhaps I can study, as was mentioned, the long-time behavior, and that's, of course, probably the most important question. But one especially can say, okay, well-posedness problem is solved. It is in this sense, but one can consider different classes, right, rather than L infinity. Okay. let's see, okay, why one wants to consider different, so what happens for theta in not in infinity, not bounded, okay? Why one wants to do this? Well, there are some reasons. One is certain kind of fluids, okay, or in certain situations, this observed theta, sorry, which is not bounded. Let me take one of these situations, for example. You have two kind of layers, so to say, I'm not sure. Okay, in one layer, the velocity is constant, say positive in this direction, and the other layer, let's say modulus of u, okay, the other layer, so it's like u, I don't know, here is E1 probably, and the other layer, it goes in the opposite direction, right? In this case, the vorticity is basically concentrated, sorry, theta, is concentrated on this line. Is positive or negative, now I don't remember, depends on the convention. It's a positive line on this, it's not an infinity, it's not even a function, it's just concentrated on this line. Okay, it's just a measure concentrated on this line. You can have also another situation, which we'll see. Okay, perhaps I can see here. You can consider a situation where, sorry, theta is concentrated in vortices, in n vortices. I think I don't remember exactly where, but this was mentioned. The n vortex system was mentioned in one of the previous talks. Okay, so basically I consider theta, which is the sum over 1 over n of vortex theta, sorry, delta of x I t, x, let's say, I start with the initial vorticity, which is concentrated in n points, okay? You can even put weights here. Sometimes you want to put weights, let's say theta I, but for simplicity here I won't do. Different, so which, right, they represent the different vortex velocities, the vortex rotation intensities, right? And then, formally speaking, at least, formally, theta t will be also vortex, will be concentrated in vortices, right? And in this case, the equation, so this is of course not an infinity case. This is a case which is relative, on one side is nice because the theta is very, on one side, the theta is very singular because it's a measure, but on the other side, you can write basically an OD for these vortices, xi t dot is equal to 1 over n, sum over j 1 to n, actually j different from I for suitable reason, xi minus xj t, okay, where I goes from 1 to n. So this is a situation where the vortex equation reduces to a basically, these are n equations, each of these xi are points in the 2D, right? So this is like point around, right? So this is a 2n dimensional equation, n-dimensional, OD. Okay, and this is you can view this as a kind of interacting particle systems because each vortex interacts with the other through the kernel. Okay. This is well known. But okay, and now let's add noise. Right? So say Q, stochastic Euler equation, or if you want, Euler equation, 2D Euler equation. Sorry, I forgot to mention the results. I should have. Right? Okay, so now, it makes sense to consider omega, sorry, theta. Omega is I don't want to say omega because it's, right? So, it makes sense to consider the case of vorticity not concentrated, not L infinity. What has been done in the deterministic world? There are some results, of course, right? For example, for omega 0 in LP, then there exists the existence in L infinity time LP space has been proven by at least Debayan-Maida, since in the paper of 1987. This, by the way, I should have told, but I didn't write the reference. Of course, is the classical result by Udovich in 1963. Thorsten next week will likely talk about this plus general form of noise one. Okay. Right, so Debayan-Maida 2086. Okay, but what about uniqueness of solution? Okay, so far it is unknown. Actually, it is unknown, but there are strong indications. Well, okay, unknown in the exact framework that I'm considering here, but there are at least two strong results, which actually 3 strong results, which are in the negative direction. One result is actually a numerical result by Bressan and Shen. I'm not sure it's published, but which show by numerics that you expect certain situation no uniqueness. So negative, say in the negative direction. Okay, some of them are really results and direction. Then there was the striking result of Vishik in 2018. Okay, again, I'm not sure this has been published, but there are notes by sort of Camillo De Lellis and co-authors, where they basically prove no uniqueness. This is numerics. No uniqueness for forced case. This then gives rise also to the no uniqueness for the Hopf in Navier-Stokes. And then, lastly, there is a result by, lastly, as far as I know, but perhaps there are other results, Elia Bruet and Maria Colombo in 2000. Again, sorry, this probably has been published, but I didn't check. Which prove, in fact, no uniqueness in the non-force case, but with the convex integration techniques. Okay, so then you say the answer is yes. Well, I say it's not exactly in the same framework because I think they work on the torus. I work on the full space. Okay. But I would say it, and okay, I cannot really say whether, yes.
Actually, there's an important subtlety there.
Okay.
So they have weak solution of Euler in the initial formulation, and they have uniform bound on the LP normal.
Ah, okay.
But if you inspect the proof, it's not they are able to prove that the velocity is actually transported by the velocity.
Ah, so you are not able.
In fact, yeah, it's not in the formulation of the dot.
Okay.
And I think if you ask them, they believe that somewhat the convex integration techniques they're using.
Ah, okay.
Makes it hard to compare the velocity with the.
So in some sense, sorry.
Well, they're not regular enough to be multiplied.
Okay, so it might be that to me that the vorticity is no longer in LP in a way. That's
the vorticity is uniform in LP, but it's not clear if it satisfies the transport.
Okay. No, I see. Okay. No.
The solution satisfies the equation in the primal sense, right? And
Yeah.
kind of derive the vorticity to that.
Yeah. Okay.
It's not even clear because
Okay.
some ability you cannot even multiply into omega.
Yes. Okay, thanks. Then this I didn't know, so okay, I have to be more careful here. Perhaps I can write in for velocity equation then, kind of.
Yes.
Okay. No, I agree. Yes.
If you ask me whether this was possible,
Okay.
some kind of, but it's
Okay. So then it's better to say, I guess, yeah, for let's say for velocity equation. Okay. Thanks. Okay. Yeah, sure.
in fact, the Deterministic.
Yes.
I think when you are very low, even there it's not completely clear that.
Okay.
But there is result by and somebody else.
Okay.
Who actually a renormalized solution of the transport equation.
Yeah, okay.
If you cut it off on the level sets, the resulting cutoff vorticity is in fact transported by.
Okay. I thought, okay, that's good, and I didn't know this. I was thinking also whether one can use some kind of Tricala-Choquet to define, but perhaps this is not possible, right? In this, a Tricala-Choquet to define the, but then it's another story.
Yeah, I don't know if it satisfies.
Okay.
Actually, their solution satisfies the
Okay.
I haven't
Okay. Perhaps I didn't. I mean, I didn't explore these things, and good that you pointed this. Okay, so perhaps I should be slightly. Let me put in the. But at least for P, I think for P equal to 2, this should be true, right?
Yeah,
P. Okay. Yeah. Okay. Yes. Okay. Thanks.
And they are like
Yeah. Okay. Thanks. It was. Okay. So one other thing that I should say, some other results. Okay, there is one result when theta 0 is, it can be more general than that, but let me say this, is a positive measure. Okay, it's h minus 1, that is to say u is near 2, u0 is near 2, but it has to be a positive, and then by standard functional analysis, this has to be a measure, so a positive measures. This is a result due to Delort in 1991. Again, we are talking about existence. Okay, existence in the class. So in the class in existence in L infinity time with values in. Okay, this I should be yes. This yeah. Okay. There is also a later result by Choquet in this 95, which was what I was mentioning before. And then there is the last result, actually an existence for all theta 0 in h minus 1. Actually, now I should really be careful because I think then the real result is, I think, for the velocity, and actually it's true in any dimension. And this is by Wiedemann in 2011, which proves that, but again, there exists existence. Now let me, okay, perhaps here I should be careful. Let me say for u in L2, u in, say, an infinity time L2. Okay, hopefully if I didn't get, okay, again by convex integration. Okay, I hope I didn't say anything, okay, hopefully. Right, okay, but nonetheless, uniqueness is unknown as soon as you, or I mean, indications are false as soon as you go below L infinity. Now, let's now add finally the noise. Okay, so but perhaps I'll change, I just put here. With the transport noise. Okay, so let's consider now, so this is, since it is a kind of continuity transport equation, with again the relation UK convolved with theta, let's add a transport noise. So plus, let's say, sum over k of sigma k times grad theta Stratonovich dwk equal to 0. Okay. Right. I see this again, you can write as div of sigma k theta, because for my, what I always consider is that sigma k are divergence free, right? Or my velocity field, my random velocity field will be the divergence free space. Okay, do we have like 40 hours, something like that? 20, okay, thanks. Okay, so, or if you want to write in a more informal way, this is just u times grad theta plus v times grad theta, d0, where v is our, it's a random, so divergence-free, random, Gaussian, centered, div-free. Div-free, and of course, white in time. Okay. Of course, right? Okay. So why we want to do so? Okay. So kind of motivations. Right. Okay. So one thing is, okay, I don't have a strict physical motivation. So if you want, part of the reason is because this noise it's something that works, right? So we make it works. But I mean, one can say that this preserves the transport nature of equation. And there is also kind of a phenomenological interpretation. As a phenomenological representation rather than interpretation. As a small scale behavior. For this small scale behavior. I mean, in the sense that the noise represents a small scale behavior, right? And this is, I refer to a paper by Franco and Umberto Pappalettera in 2022. Well, they basically prove that if you represent certain small scales as Brownian noise, okay, and then you do some scaling, then you get this transport equation. I say this is phenomenological both because, okay, why small scale should be Gaussian, it's questionable. And second, because it's not, okay, it's true that they divide in the proof they divide the velocity in two parts, small and large scale, right? But then this is a priori division, right? One should a posteriori prove that, in fact, what you get as a limit of large scale keeps being large scale, right? Which is something which is difficult to do, right? And as far as I know, it is unknown, right? But nonetheless can be an indication. And there is also, and perhaps Thorsten will talk a bit more about that, so let me just write it also here. There is a geometric or variational viewpoint we started with the paper of Derry-Holm in 2015. Okay, perhaps this will. And okay, the last point is, since we tried transport noise works very well for regularization by noise, why not to try those noise here, right? Yes. Not that I know. No, not that I know. But you think it's like K plus something. Not that I know. Not that I know. Okay. It would be kind of nonlinear noise in the end, because then the velocity would be, yeah. I mean, so Euler equation plus even multiplicative noise, this has been studied, but not in the form, as far as I know, not in the form that you said. Okay. I mean, okay, there are a lot of results that some of them were mentioned before, well, not about Euler, but about Navier-Stokes by kind of non-regularization by noise. Perhaps this is by, so of Manova and Su. Okay, these are kind of in the negative direction. Okay. But anyway, the first things, so let's ask about the question of regularization by noise. Okay, the first things that we want to try is, okay, let's try with a very simple noise, right? Like in a stochastic continuity equation, which perhaps I erased here. Just at the Lagrangian level, this is purely additive noise, so just plus dW. At the Eulerian level, let us try, so first attempt, try just, let's say, sigma k, just ek, which is to say, basically, the noise that we have is just grad theta Stratonovich dW, for W, which is a d-dimensional boundary motion. Okay. This already worked in the linear setting, so why not to try this? Absolutely no regularization by noise. Okay. And why it is so? Well, just make a change of variable. Okay, let's take theta tilde tx equal to theta t x, say x tilde just because x tilde plus wt, and prove it as an exercise that d theta tilde satisfies the equation plus k convolve theta tilde times grad theta tilde equal to 0, exactly the Euler equation. Okay, so this noise does essentially nothing. It's just change, just adds like a change of coordinates of Lagrangian coordinates, right? Then you cannot expect anything to change because you just go back to the classical Euler equation, right? Okay, so let's try now something perhaps more complicated, so more, let's say, yeah, no, not as easy as that. Let's try sigma k to understand what happens. Let's try sigma k, say non-constant but smooth. Right? So this was the case where somehow, if you want to write it, if you like, more kind of deterministic way of thinking, this I'm just saying that this is just v of t, it just doesn't depend on x. Here I'm saying that v of t of x is smooth in x. Okay. 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 Now, instead of trying to do this at the level of the Euler equation, let me go back to a simpler system, the vortex system, because this is an n dimensional, so we can try to do computation with that, and that's perhaps easier. So let's consider the try with vortexes. Sorry, perhaps you don't read here. Try with vortex systems. Okay, the xi. So the deterministic part looks the same. To say actually, okay, yes. Yeah, fine. But then the stochastic part is just as following. It's just we are adding the noise on the level of the particle xi, I don't know, dwk. Right? If you want, this is just again v of txi, if you like this notation. Right? Now here we see that what the problem is. Also in this case particularly we see, okay. Okay, so the point is you see k here is singular, well, the drift so to say, not k. Drift is singular on the diagonal, xi equal to xj for some I different from j, right? Because the kernel k is singular. Now, if you remember, the idea of regularization by noise was, one of the idea possible, is to say the noise is very strong, the noise is dominating the drift in a way. Okay? Now, let's see what the noise does at the singularity. The singularity is the diagonal. Let's compute it. Well, let's say on the, not the, I mean, let's say, yeah, well, the diagonal, perhaps. So let's consider the noise rather than on the diagonal, say in the singular direction. In singular direction. Xi minus xj, right? So you want to prevent this to, well, either prevent, yes, you would like to prevent this or anyway control this, what happens when this comes very close to zero, which is the singularity, okay? But this singular direction at xi equal to xj is actually degenerate. Right? So, in other words, you can say that sort of v, let's say, sum over k of sigma k of xi Stratonovich dwk minus sum over k of sigma k xj Stratonovich dwk, this is nothing but, this is roughly speaking of the order xi minus xj. Okay. In space, forget about time. So in particular, when two particles come close, which of course is something you would like to have, not to have here, the noise is exactly the same on the two particles and will not move will not move them away, right? So that's the problem. That's why, in some sense, the nonlinear case, at least for nonlinear transpose, is different and much more difficult than the linear case, because in the case, if we consider nonlinear case, usually there is some form of interaction, okay, in when two particles collide. And unfortunately, the noise is not a kind of elliptic noise, but is degenerate exactly on the direction that where we would like to have regularization. Okay. And so now I hope that I want to give, so I want to reconcile somehow they're not reconciled, but now I can connect with the Kraichnan noise, at least kind of ideally, with I mean, intuitively. What I can say is that, okay, what if I want to pursue the idea that I want to have a strong noise against the singularity, okay, I want to kind of have less singular noise when x is equal to y. So, okay, which amount to say, so I want to have the noise which is, yes, less singular, is, so I want to kind of tame these x minus y, xi minus xj. And so I want to take something which, for example, goes like, so wanted sigma k, so sometimes vtx minus vty to be much larger than x minus y. Anyway. This is where exactly the Kraichnan noise, the non-smooth Kraichnan noise comes into play. Right. Of course, I mean, you can say that this is very naive, right? I didn't use any structure of the equation. For example, K maybe like in Keller-Segel could be even attractive, so it could be much worse. So I didn't use this structure. So this could be naive, and indeed there might be other ways to do this better. Actually, there is a result which does this better for exactly for n-vortex systems by Franco Flandori, Massimiliano Cubinelli, and Enrico Priola in 2011. It's not the same paper, it's actually the paper called Full Well-posedness, somebody, it's not the same paper 2010 that I quoted before, where they prove that actually the n-vortex system with the smooth noise now, with smooth but non-degenerate noise, smooth, let me write non-degenerate, yeah, I mean, kind of there is a Normander type condition, outside the diagonal, non-degenerate, but I don't want to specify noise, is actually well-posed for every initial condition. There is actually a result. Why I say for every? Because there is a result by Marchioro and Pulvirenti. Here actually now, to be precise, actually this is, for conservation laws, this has to be, this is actually well-posed for every initial condition as well, even without noise, for essentially a conservation, because it's a Hamiltonian system. When you put now possibly positive and negative vorticity, here I have to put weight and things change it, and there can be configuration where this, like a 3-vortex configuration where this collapse. Okay, something you don't like. Basically, Franco, Max Cubinelli, and Enrico Priola, they prove that this does not happen. So, but these configurations are very rare, but they do exist. Franco, Max Kubinelli, and Enrico Priola, they proved that this does not happen with noise for every initial condition, right? So it was a bit fast, but so to say that there exist other results as well. Okay, now I want to finally state my result, and I will prove tomorrow. Okay. These three. Main result. Okay, it's due. Okay. So let me now consider QD Euler plus Kraichnan plus non-smooth Kraichnan. Theorem. No, sorry, let me first write the equations. d dt plus u times grad theta dt plus sum over k of sigma k x Stratonovich dwk equal to 0, where you can call this again, think of v of t, sorry, not to the capital X, small x, sorry, transport, I forgot that. Sigma k times grad theta, so the same, but now this is v of t of x, but now v is actually Kraichnan, no smooth Kraichnan. So v, so let's see, you can write in two ways, equivalent way. So this one, the covariance matrix is now, sorry, I have to go, q of x minus y, and this q is exactly the no smooth Kraichnan, right? So q of no smooth. Right, which is to say q hat n is n to the power minus d minus 2 alpha I minus n transpose over n square. Anyway, the input alpha has to be between 0 and 1. Now here's our result. I will just write by Michele Kogi and myself in archive last year, right? Where we prove as follows. I will just directly give, there are two results, I will just give the one on about uniqueness first. So this is uniqueness in LP. So let's start with omega 0, sorry, theta 0, which is initial condition in LP. Okay, and then I have to put L1 just because I don't want things to happen, bad things to happen at infinity, and for technical reason also in H dot minus 1. And the condition on P is P, okay, smaller than infinity just because I don't want the trivial case. And I need also alpha to be smaller than 1 alpha, the regularity index, and smaller than 1 minus 1 divided by P. These are the structural conditions that we have with our proof. There are also some technical ones which we were not able to avoid, so but then they were avoided by a later work. And this is larger than 0 and also 2p minus 1. Okay, but the true one are these. Well, okay, this one is not. This one, this relation. Right? Then it's done. Okay. There is strong existence and pathwise uniqueness. Just write this above just because I don't have space. 0, 2p minus 1. For this is before Euler plus Kraichnan. Okay, Euler plus Kraichnan. In the space, the space is essentially this one. An infinity time and random variable with respect to LP and L1. Technically, I have to add something more. Okay, there is the condition that has to be essentially in H minus 1, just to define the H dot minus 1, just to define the convolution, otherwise you may have problems. And also, I will, this I want to specify. I have this, right, this existence in H minus alpha, okay? This is of course true if p is equal to 2, this is automatic, right? Because then LP cap L1 is contained in yes, it's contained in H minus alpha, but if p is low, then this might not be the case, right? So this I need to this condition. How much time do I have? Basically 0. Okay, yes, I don't think I will mention the second result. Let me just mention that this result is not, I mean, it's not known and perhaps false in the deterministic, one does not know in the deterministic case, so you really have, you really now can show that for the two-dimensional Euler equation, there is a regularization by noise effect. So for in the LP, the equation with noise, with this Kraichnan noise, is well posed under suitable regime, of course, with alpha, right? There is an extra thing that I want to say, and then I conclude. Yeah. So even there is, we will see in the proof that one crucial step, actually, perhaps yes, one of the two crucial steps, is to show that the Kraichnan model, even itself, without noise, has an anomalous regularization effect in terms of negative Sobolev space. Okay, this is something that may be interesting on its own, even if you are not interested in the Euler plus Kraichnan. So in the next proof, we will show, the proof will be based on two facts, essentially, that we have this anomalous regularization for Euler plus for Kraichnan, and then, okay, in terms of negative Sobolev norm. And then we will see that this is actually true also for Euler plus Kraichnan. And so this actually amounts, this will then give us the uniqueness statement, and we also allow to improve the existence result in the deterministic case. Okay, thanks. Sorry for being late. No further. Right, sorry, yes, I didn't mention. I mean, it's the same relation in the deterministic case. So theta t is 1 over n sum over I, and it's the empirical measure. Right? Okay, it's just that this is now random, of course, because these are as well random.